Data Science with R, sponsored by SimplyLearn. That's www.simplylearn.com. Get certified, get ahead. My name is Richard Kirschner, and I'm with the SimplyLearn team. What's in it for you? We're going to go through an introduction to R, why R, CRAN, Comprehensive R Archive Network, and cover installing R. Then we'll get into simple linear regression using R, line of best fit using error summation, correlation analysis in R. And then we'll get into classification using R. Use case, predict the class of a flower. Let's start with an introduction to R. First, it's an open source. R is completely free and open source with active community members. Extensible. It offers various statistical and graphical techniques. Compatible. R is compatible across all platforms, Linux, Windows, and Mac. Library. R has an extensive library of packages for machine learning. Easy integration. It can be easily integrated with popular softwares like Tableau, SQL Server, etc. This only touches a little bit on these different aspects of R. The fact that it's it's very extensive. It probably has one of the most extensive set of data analysis packages currently out. It has a compatibility that is continually growing, so it's integrated with everything from cluster computing to Python integration, which is now coming out. And its extensive libraries allows you to import the different libraries to use for whatever your needs are. Makes it a very diverse and easy to use coding source for analyzing data. R is more than just a programming language. As I just touched upon it, it has a worldwide repository system, Comprehensive R Archive Network, and it can be accessed at https://cran.rproject.org. It provides up-to-date versions of code and documentation for R. CRAN hosts around 10,000 packages of R. That is a huge repository focused on just data analytics. Let's install R to get started. You can easily download the executable file for R and install it from CRAN website. If you go under the downloads, in this case since I'm on a Windows machine, we'll walk through it from the R 3.5 version for Windows. So here we are at https://cran.r-project.org, and you can see down here we have the different options for the downloads. If we go under Windows, which is I'm on a Windows machine. If you're on a Mac machine, you can do the Mac or Linux. There's install R for the first time. Just click on that and open and run it. The installation is pretty simple. Follow the default options to finish the installation. After the installation is complete, you'll see the R icon on your desktop. Alternatively, there are mirror sites, and so we can go into RStudio. Let's just take a quick look at that. If you're on the RStudio website, that's www.rstudio.com, you can go down under Products and RStudio Download. You'll see a number of options here. The first one is the RStudio Desktop Open Source License. That's the same thing, you just download it. So if you download that, that's what you're getting. There's also an open source server setup, which is also free, you can download from here. And then RStudio offers a number of paid packages, which includes all kinds of different supports for company and individual level setup. Whether you go through the CRAN site or the RStudio site, the installation is pretty simple. Just a quick note, if you're a Debian distribution, including Ubuntu, you can install R using its regular package management tools. And when you're using a Linux system, that is preferred because then it registers it properly on the setup system. Let's go ahead and open up our RStudio and take a look. Here we are, and I've opened this up in the RStudio version, which automatically opens up some extra windows, which is nice. Let's go ahead and take a look at that. We have our console on the left. This is your main workspace. So if I go in here and I do, click the mouse, and I do a 4 plus 4, it'll come up and say the answer is 8. And you have some environmental information, and over on the right you have plots. Usually when you're working in here, let's do a script. We'll go up here into the plus sign in the upper left-hand corner and just add some script in here. In this case, it showed up on the top, but you can move these windows around. And let's say I do y equals 3 plus 4, x equals y plus 2, and then I'm going to do just x. And let's do a plot. We'll throw a plot in there. C is a notation that these are going to be Cartesian points. So we got 1, 2, 3. That'd be like your x. And then y, 3, 4, 5 for just a standard call scatter plot. You don't have to memorize this. We'll go into some of this later on. And then I can take all of this. If I go under code, since I'm working in the code console, and I go down to run, region, and just run all, it takes this code and just runs it through my console. And you can see down here, it's executed y equals 3 plus 4, x equals x plus 2, and if you add 3 plus 4 plus 2, you get 9. That's what the x does. And then I did a plot. I threw the plot in there, where I'm plotting 1, 2, 3, 3, 4, 5. And if you use just a straight plot, it's a scatter plot, and you can see that this appears on the bottom right, where you have your plots coming in. So it's a very quick way to show data. And that's one of the wonderful things about R, is it's very easy and quick to go through and do different functions on the data and analyze it. So it's a very popular package. Before you start programming in R, you should install packages and its dependencies. Packages provide pre-assembled collections of functions and objects. Each package is hosted on the CRAN repository. Not all packages are loaded by default, but they can be installed on demand. Remember earlier we were talking about all the different packages available? You don't want to install everything from R. It would just be a huge waste of space. You want to just install those packages you need. So to install packages in RStudio, you go under Tools and Install Packages. When you click on the Install Packages, you'll get a dialog box. You'll see where it has a repository CRAN, because there's other repositories, and you can even download and install your own packages you can build. And then you'll pick out the packages you want and separate multiple with spaces or commas, so you can install numerous packages at the same time. In this case, we're installing the forecast package, and you can see down here I just type in forecast, install all the dependencies, so it uses other packages to build on. It has those, and then just click on install and it's done. Before we cover the basic linear regression model, let's just take a quick look at some of the different parts of R, or parts of programming you'll need, or scripting. First, you need to know there are various data structures in R. We have vectors, we have matrices, we have arrays, data frames, and lists. Vectors is the most basic data structure. If you remember, vectors are a location and a direction is how they're generally defined. Although vectors, when you're talking about scripting, can contain numerous different values. You could have vectors with 4, 5, 6, 7, 8 different values in it. For example, a picture on the computer might have the location of the pixel and the number for the red hue and the green hue and the blue hue. So now you have something with 5 different numbers in it consisting of that vector. Matrices allow you to move stuff around. So you might have a 2 by 3 matrix that you switch to a 3 by 2. We looked at an XY plot earlier. It might be that you have everything you have 10 different numbers and each one has 2 values, XY, and you need to switch that matrix. So then you have 2 arrays of 5 numbers. Arrays are just that, a collection, and you can have arrays of arrays of arrays. Data frames have labels on them, which makes them easier to use. So usually we use a lot of data frames when we're working with data because they're just easy. You can have a column and you can have a row. So think of rows and columns when you see the term data frames. And then lists are usually homogeneous groups. So in R, you're usually looking at similar data that's connected in the list. So the first thing we do before we're even importing the data, you should have the data ready. So we need to look at the data and see what's going on. You can import data from various sources, including Excel, Minitab, CSV, table, text files. CSV is usually a text file, comma separated variables, tab separated variables. There's all kinds of different options here. And importing the table is very simple. We have table, read table, file equals, data table, header equals true. And let's just take a closer look at what we're talking about here. Scratch the closer look. I didn't realize it was just for example. So importing a table file is pretty simple. You read.table, file equals data.table, so whatever the name of the file is, comma, header equals true, so if there's a header to it. In this quick flash they have name, age, gender. We'll actually do this in R with another data set in just a minute. But you can see it's very easy to read. A lot of people use R even in other programming languages so they can quickly look at the data before they even start analyzing it. CSV file, same thing, read.csv. File equals data CSV, header equals true, separation equals space. So in this case, even though CSV stands for comma separated variable, this one is separated by spaces, and they have the header, name, age, gender. So it's the same file, saved as a CSV file. And there's also Excel. Excel has its own issues as far as making sure you know what the tables are and the headers are. But you can see that each one of these is easy to import. So, and just like it's easy to import the data, you can also export tables in R. So you can see here, write.table, my file, see my file.txt, comma, separated. And the scoop T just means it's tab separated. So if you're using tabbed files on there. Example, Excel. So you can write a .xls to my file. In this case, they did a text separation equals scoop T, so it's a tab separated for Excel file. CSV, same thing. Very easy to write a CSV file to your computer once you've changed the data or altered it depending on what you're doing with it. And once we have our data imported, and we can save it afterwards and export it, graphing. Visualization in R is very powerful and it's quick. Love doing this before even exploring the data. Sometimes you just want to graph it to see what it is there so you have an idea of what you're looking for. So graphics in R cover a huge amount of different things. R includes powerful package of graphics that help in data visualization. These graphics can be viewed on screen, saved in various formats including PDF, PNG, JPEG, WMF, and PS, can be customized according to very graphic needs. You can copy and paste in Word or PowerPoint files. R supports various types of graphics including bar chart, pie chart, histogram, kernel density plots, line chart, box plot, heat map, word cloud. There's even some more obscure ones, but these are the main ones that most people use. I know I use a lot of heat maps, but word clouds are a lot of fun if you're doing websites and data and word analysis. And then histogram is very popular. All of these are very widely used. Let's look at the box plots, also known as whisker diagrams. Box plots display the distribution of data based on minimum, first quartile, medium, third quartile, and maximum. So right off the bat, we can use a box plot to explore our data with very little work. To create a box plot, we simply give a box plot and the data. Very straightforward. So we might have passenger numbers in the thousands. I guess this is exploring data dealing with airplanes. And you can see here they just have a simple plot. If you break it down, you have your, if we go back one, you'll notice we have like a minimum, a maximum, our medium, first quartile and third quartile. Let's just break that apart. You can see the line on the bottom is your minimum, your line on the top is the maximum. You have your medium and your first quartile right there. First quartile and third quartile. And the way a lot of times you read this is things that are above the box are outliers and things below the box are outliers, and what's in the middle of the box is usually the data you're looking at. Linear regression. Now we have a few tools of what R can do. Let's look at the theory behind linear regression and how that applies to what we're going to use in R. Let's understand more concepts by solving a few algorithms. Firstly, linear regression, which can be applied in two ways. One, we can estimate the relationship between two variables. Does body weight influence the blood cholesterol level? So we just want to know if it's even a valid connection or not. Will size of the house affect the house price? So we can estimate the relationship between two variables also. And then we can predict the value of one variable dependent on the basis of other independent variables. So once we know they're connected, we want to use that to go ahead and predict it. In the cases above, maybe the body weight versus cholesterol. So the higher the body weight is, probably the higher cholesterol. So first we explore, is there a connection? And if there is, can we actually apply that to a linear regression model where we can see how they're connected? Same thing with house pricing. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. Y being the dependent variable, x being the independent variable, m being the slope of the line, which you can see over here on our graph, equals y2 minus y1 over x2 minus x1, and c being the intercept, or the coefficient of the line. Now, you don't have to memorize all the formulas we're going to go in here, because most of R does this for you. But you do need to know what's going on in the back end so that you can understand if it's working or it's not working, where the problem lies. Types of linear regression. There's simple linear regression. Considers one quantitative and independent variable, x, to predict the other quantitative but dependent variable, y. And that's the formula we just saw. y equals m times x plus c. And then we have multiple linear regression. Considers more than one quantitative and independent variable. So instead of having just x, you have x of 1, x of 2, x of 3 to predict the other quantitative but dependent variable y. So instead of looking at just body mass, we might also look at height. So you have body mass and height would be two independent variables. Housing prices might have to do with the distance to a certain area. So location might be one of the variables along with the size of the house. Let's consider a sample data set with 5 rows and find out how to draw the regression line. So in here you can see we have independent variable and our dependent variable, where we've taken some random data. In this case we have 1, 2, 3, 4, 5 for x, and we have 2, 4, 6, 5, 8 for y. And the first thing we do is we might plot it. If you look at the plot, you can see that it has a nice line through it. Just eyeballing it, you can guess that there's probably a linear regression model that will fit this data. Then we go ahead and calculate the mean. We count the mean of x and the mean of y. And you can see that we plotted that on there, 3, 5 for this particular data set. And so drawing the equation of the regression line, we'll go ahead and take a summation of x, a summation of y, take a summation of x squared and a summation of y squared, and then x times y. And this is why it's so nice for the computer to do this work for you, because I don't know about you, I hate sitting there with a calculator, and if you have just 5 variables, that would be very long, not a big deal, but if you're doing hundreds of variables, definitely much easier to let the computer do it all. So the intuition behind the regression line breaks down to the linear equation, which is represented as y equals m times x plus c. In this case, m equals this very lengthy formula where you have your summations. So all the values that we've already computed fit right into this equation. And so you have n being the number of variables, that's what the n stands for. Your x times y we computed, the sum of x, sum of y over the number of variables times the sum of x squared minus the sum of x squared. And then, of course, we have, you put the numbers in and you get a value of 1.3, and you find out that your c is equal to 1.1. And once we have this formula, we can easily compute the y values. Y equals m times x plus c equals 1.3 times 3 plus 1.1 equals 5. And this would be the example of x equals 3. You could also put in x equals 6, an unknown value. Let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 1.3 and c equals 1.1. So here's our regression line, and then you can see if we put in all the numbers 1, 2, 3, 4, 5, we don't get the exact prediction because it's a line through the data. You'll see that it's ever so slightly off, 2.4, 3.7, 5, 6.3, 7.6. But it is a good estimate of what the data is going to generate. Let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 1.3 and c equals 1.1. The best fit line should have the least sum of squares of these errors, also known as e square. The predicted y value, residuals of errors, the actual y values. So one of the things we're looking at when we put this information together is we want these distances to be minimized, so it has the smallest amount of error possible. Let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 1.3 and c equals 1.1. And here you can see we've done the same kind of chart. We have our y predicted, and then we have the actual y minus the y predicted, because we are looking for the error squared or the e squared values. The sum of the squared errors for this regression line is 3.9. We check this error for each line and conclude the best fit line having the least e square values. Minimizing the distance, there are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. And no matter how you compute the errors, you can see here this is what it's basically going through. It's taking the line and slowly adjusts it until it has the minimal error available, the minimal distance between the line and the different data points. Use case. We'll start with linear regression, and then we'll jump in and also do a decision tree, so you can see how they are same and how they differ in the way they function and what they're used for. And while we're going through the use case, you can start linking the theory behind it connected to the actual use. And as you connect those dots, you can see that by making changes in the model based on the theory, you can also fine-tune it. We'll talk about that briefly as we go through this. For this analysis, we'll use the default CARS dataset to find the correlation between variables. Cars is a standard built-in dataset that makes it convenient to show linear regression in a simple and easy to understand fashion. And we'll start with head cars and string cars. Now I've gone ahead and removed the script on here to make this easier to see, and we don't have to do any kind of importing of data because it's already in there. I'm just going to type in head and cars and hit enter. And what you're going to notice is it's going to display the first 6 rows, 1, 2, 3, 4, 5, 6, and you'll see speed and distance. Now this is a little bit like a spreadsheet, so if you're using an Excel spreadsheet it should look the same, and this is a standard data frame kind of setup. In this case, whenever you say head, it usually lists the first number of rows, depending on your package. In R, it starts with 1, and then it does the first 6 rows. String, when we do a string of cars, it's going to break it down and show us that it's a data frame. It has 50 objects, that's with the 50 OBS, of 2 variables. And then we have speed. The first variable is going to be a number, is what NUM stands for, 4477, it just starts listing the data there. And distance. Now I'm assuming the speed is the speed of the engine. Otherwise, if it's the speed of the car, then the distance should always be the same, and that would just be kind of silly. But this is the speed of the engine, and based on the speed of the engine, can we correlate that to the distance? Let us visualize the data using scatterplot to understand the relationship between predictor and response. And I want you to notice that in this slide, a line has been drawn through the data. Now when we first start with data, you don't have that line. So as we plot it, I want you to kind of visualize that line there and just kind of say, hey, does this stuff kind of scatter around a line or not? Before we actually create the model. And we simply do plot, and I'm going to do a shorthand here, cars, and I hit enter, and it comes over here to the right and plots our data for us. Now because there's only 2 variables, I don't have to do anything special. I'm going to expand this over environment so we can see it. And you can see you can just visualize a line right through the data, and it's all clumped along that line, which makes it really nice for doing a linear regression model. Now I did something a little tricky here because I'm very lazy. I typed in plot cars. A lot of times you don't want to do that because you don't want to plot all the data. We could do plot, in this case cars, $, speed, the first variable, cars, $, distance. When I do that, I get the same plot. All I'm doing is telling it to use just these 2 columns of data. And although the first one is quick and easy, if you only have 2 columns of data, the second one is what you really want to do when you're plotting data like this. You want to control which columns you're using. And then we want to do a correlation. Correlation analysis studies the strength of relationship between 2 continuous variables. It involves computing the correlation coefficient between the 2 variables. If one variable consistently increases with increasing value of the other, then they have a strong positive correlation, a value close to 1. And again, I can just type in correlation cars, the short form, and we can see we have a nice correlation going on there between the 2. What we really want to do though is we want to correlate cars, and then we're going to do the speed, comma, cars, and the distance. And so when you look at this, I actually hit the enter key in the middle of that, which is fine. You can, in R, do it line by line. So if you're trying to do a bunch of different columns, you might want to do that to make it easier to read. And you can see here I get the point 806894. The closer this is to 1, the more these correlate. So it's saying there's a pretty good correlation, positive correlation between the 2 variables. And if you look at it when I did just cars, which did the correlation over all the variables, you'll see that speed correlates with speed 100% because they're the same. That's just the nature of that. But when you look at speed versus distance, we get the point 806849. And if you do distance to distance, you get also 1 since they're identical variables. So now it's time to build our linear regression model on the entire data set to build the coefficients. Let's just take a look and see what that looks like. Back in our console, I'm going to type in linear mod. And in R, we want to do the arrow, kind of like an arrow in a line, or in this case, the less than minus sign. That's the same as assigning whatever we're going to put after it to this variable. So we're creating the linear variable. LM stands for linear module. And we're going to look at speed and distance. So we put the little squiggly bracket between them. This lets R know we're going to deal with these 2 columns, comma, data equals cars. And when I hit enter on here, we've generated our linear mod. Now we want to go ahead and summarize it. And we simply do a summary and then brackets, linear mod, and it generates all kinds of information on our model so we can explore just how well this model is fitting the data we have right now. Now if you've done linear regression in other packages and scripts, you're going to see that this is so easy to explore data in R. So even somebody who's working in, say, Python or or Spark, Hadoop, coming back to the R console to do some basic exploration of the data is very beneficial. And if you use just R goes into all kinds of different packages, and you can even do cluster computations through H2OR. There's a lot of cool things. This is what makes R so wonderful, is how easily we can summarize something like a linear model. And to explore this data, let's go back to the slide. And we'll see here where it says the residuals, the first 1Q stands for first quadrant, median, third quadrant, max, coefficients. And we first want to do is look at the estimate standard deviation on here. And you'll see the intercept is at minus 17.5791 and speed 3.9324. So we can compute the distance equals to the intercept plus the beta times the speed, which just means that we can assign a distance equal to minus 17.579 plus the 3.932 times the speed. The value of p should be less than 0.05 for the model to be statistically significant. And this is one of the things I love about R. You can see right down here, we punched in the numbers and it even tells you the significant codes. So if you're trying to guess or remember, it tells you right away, hey, this 1.49 to the minus 12th is way below 0.001 on there. And it even puts 3 stars next to it, so you can see that that is a very high correlation. And you can see the 0.0123 gets 1 star because it is greater than the 0.05, or it's less than the 0.05. So this shows that there's a very high correlation. Statistically, it's very significant. So now we're going to go ahead and create a training and a test data set. And the first thing we want to do is we want to set the seed so the sample can be recreated for future use. Remember, in all these different regression models, they usually have some randomization going on in the back to kind of fit it and guess where it's going to go. And if you want everything to match, you want to start with the same seed in that randomizer. That way it recreates it identical every time you run it on a different computer. And just like working with data in any package, we're going to create indices for the training data, and we're going to model the training data, and then we're also going to do the test data and build our model on the training data. And let's walk through that and see what that looks like in R. And I'd actually mistyped that one. Let's type in set.seed to set our seed for the 100. Let's go training row index, and that's our name we're making up for our variable. And we're going to set that to sample. Now, sample is a command in R, so we're going to take a random sample of some of the data. And then we're going to do 1 colon in rows cars. So this is the number of rows in cars, and we're going to start with 1 and sample them. So row 1 of the data. We're skipping any of the titles on the top. And then in the sample, it has 2 variables that go in. The first one is the in rows of cars, and then we want to do 0.8 times in rows of cars. And this basically says that we're going to take 80% of all the rows in the car sample. And we'll hit enter to go ahead and run that. And we see here that I had an error, and that is because it's in row. Actually put an S on there. That's something I do a lot on. We'll just fix that real quick. Brings up a point that if you use your up down arrow, you can quickly paste through the last things you typed in, and then you can reuse them. So there we go. Now I have our training row index, which is basically a list of all the rows we're going to use. And now that we have a training row index, we'll go ahead and create our training data variable. And we'll assign that cars, and we'll put that as a training row index. And this is supposed to be brackets because we're dealing with a array type format. We want to do the training row index, comma. So we just need the index of the row, and as far as the columns, we want all the columns. So here we have our training data. And now we set up a training data, we also need our test data. And with our test data, we'll assign that also to cars. And because we used the training row index and we used the sample to create it, we can simply do a minus sign training index, comma. So it's identical to the training data, but the test data is going to be the rows that were not included in the random sample of 80%. So it's going to be 20% of the data. And of course, it's very easy to do mistakes on here. So we'll come back into this, bring back up the error, and then we have training index, training row index. There we go. Very easy to correct errors in R. So now we have our training data and our test data. So we have 80% in training data and 20% in test data. And let's go ahead and create our model. We'll call it LM mod. And this is identical to what we did earlier. Here's our linear model. We're going to have our two different columns. If you remember above, we had to tell it which columns we wanted. And we're going to do distance and speed, and then the data we're going to set equal to training data. So as opposed to doing all of cars, we want to use just the training data on here. And now that we've created a model off of the training data, we need to go ahead and run our prediction off of our test data. We want to see how the test data, which has nothing to do with the model so far, how well it fits. And we'll go ahead and call it distance predict. There's our assignment, so we're going to assign the value to it. And with R, we type in predict, and then we called our model. We go ahead and pull up our model, LM mod. And so we're going to use that model, and then we want to put in the test data. Here's our test data. And so now we're creating the distance predict variable, and we're going to put all the information as far as predicting on our test data. And we'll run that. Just hit the enter key. And then, if you remember from before, we want to review the model diagnostic measures. And so we're going to go in here and do a summary. And you'll see in here we have a couple different things going on. But let's go ahead and take a summary of this and just walk through what this means. So summary, and then we call it LM mod, and we hit enter, and it pulls it up, and we have a nice summary of our LM mod. And the first thing we're going to note is that the data that's right now in our LM mod that we're summarizing is our training data. And let's go back to the slide and highlight this. So the data equals the training data. That's where the LM mod comes in. Residuals, we have our minimum, our first quarter, medium, third quarter, and the max, or quadrant, not quarter. You'd think I was doing a business analysis as opposed end of the year taxes in first quarter versus quadrant. We look at our coefficient. We can see where our intercept is and our speed is. And we note over here our significance codes, so they all match up. So a simple correlation between the actuals and the predicted values can be used as a form of accuracy measurement. So we take a look at the model we created, and now we need to take our predictions and just see how accurate it is on the data that we didn't use to program the linear model. So let's create a variable called actuals underscore predicts and assign it data frame. This is how we create a data frame, is we just assign data.frame, and we'll do a cbind. And in our cbind, we're going to take our data and we're going to create a column called actuals. So this is our choice, the name actuals. This is going to equal test data, and then we're going to use a $sign and distance. And we're running out of a little room there, so let me pull this over so we can see it better. There we go, distance. And then we also want to take and compare that to what we predicted for our other data. And we'll call this column predicteds, and that's going to equal our distance predict. And remember, distance predict is set to the predicted values of our test data. So what this is we're saying, hey, here's our test data, the actual data, and the distance, and then we have what we predicted that distance to be. And we'll go ahead and assign that. And we can do a quick head, actuals predicts, there we go. And remember, head shows us it's a data frame, so it's going to show us the labels and the first set of data. In this case, you'll notice that the rows have a different count. They're not 1, 2, 3, 4, 5, 6. Well, we randomly picked 20% of the data. So this is the first 6 rows of that random selection, which comes out as 1, 4, 8, 20, 26, 31. And we have the actuals, so the actual value is 2, and the predicted value on this first one is -5, so they're way off. 22, 7, 26, 20, 26, 37, 54 to 42, 50 to 50. So one of these is actually pretty right on, where a lot of them are really off at the beginning. Let's just see what that looks like though, because just eyeballing the first 6 rows does not tell us what's really going on. So let's create another variable, correlation accuracy, and we're going to assign this correlation, COR. Remember, we do a COR, and we have our actual predictions. So let's just see how our actual values versus the prediction correlate with each other. And we assign that one, actuals underscore predicts. There we go. Let it auto finish for me. And we can just go ahead and type in correlation accuracy and see what that looks like. So we have an actuals 1, a predicts 0.8, and you can see how they kind of correlate. We have the 0.82, and if you remember from before, we're looking for either 0.001, 0.01, 0.05, 0.1. That is the p-value, which we're not looking at here. This is not based on the p-value. This is based on what we looked at earlier with correlation, that the closer to 1, the closer the values are. And so 0.82 gets upwards of 1, so you see that there's a normal, pretty much a correlation in here. But we want to dig a little deeper because this doesn't really tell us how accurate it is. For that, we're going to use another tool. For that, we're going to calculate the min-max accuracy and MAPE. And the min-max accuracy equals the mean value of the minimal actuals and predicts over the max value of the actuals and predicts. And then the mean absolute percentage error, or MAPE as it's called, equals the mean of the absolutes predicteds minus actuals over the actuals. That's a lot to follow as far as remembering all these different math and theory behind it. Cool thing though is it's all done pretty much for you. So you can compute all the error matrices in one go using the regress eval function in DMWR package. Since this is the first time I've used this install, I'm going to have to install the DMWR package. So we can actually install it two different ways. If you remember, we talked about installing package earlier. We can go under Tools and Install Packages, and I certainly could type in DMWR. It even comes up and lets me know that's one of the main packages up there. Well, that's a tool of the RStudio setup. You can also install this using the console. We simply type in install. You can even see here it comes up install packages and then DMWR. And when I hit enter, it should do the same thing as the other one does. It goes through and installs the DMWR package. And it takes just a moment to zip through all the different package setup. And then the format for DMWR is DMWR. We're going to go : We are specifically looking at the regression.eval. And then we're going to do actuals _ predicts. And we'll go ahead and put in the individual columns on this one. So we have actuals. I love the auto typing. And then again, actuals predicts. And this time we want to do it against the predicteds. And we'll go ahead and hit enter on here. And you'll see in here it comes up with our MAE, MSE, RMSE, and the MAPE values. So we looked at the linear regression model. Let's go ahead and take a look at the decision trees. So let's go ahead and talk about another algorithm, decision tree. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. It is a tree which helps us by assisting us in decision making. Let's look at the basic terminologies to understand decision trees. We have our root node, we have a splitting, we have decision node, and then those split into terminal node, decision node, terminal node, terminal node. And each decision node continues to split until it ends in a terminal node. Note, A is the parent node of B and C. Also note we call the terminal nodes leaf nodes. You can also see that we have a branch or a subtree. So when you have a split, everything under that split under one side is called a subtree. You cannot build your decision tree without knowing entropy and information gain. Entropy. Entropy is the measure of randomness of impurity in the data set. So we have here a bunch of fruit, and you can see we have, it looks like apples, oranges, and bananas. It's very chaotic, so it's a very random data set. It has a very high entropy. And if we take out one group, let's say we take out the apples, it's a little less random. Now we only have bananas and oranges. So it's a less random data set, and we have lower amount of entropy. Entropy is a measure of randomness or impurity in the data set, so when you have a homogeneous data set, we will have entropy equals 0. And here you can see it's all oranges. An equal divided data set will have an entropy equal to 1. So here we have half, or what is it? It looks like a couple bananas, a couple oranges, and a couple apples. So everything is equal. So we have an entropy of 1 on there since there's 2 of everything. Information gain. It is a measure of decrease in entropy after the data set is split, also known as entropy reduction. So we look over here and we have an entropy equals E1, and the information gain as we split the bananas out, the size becomes smaller, and you'll see that E1 is going to be greater than E2, or we measure E2 of the apples and oranges in this case. If you love your fruit, it's probably getting you hungry right about now. And then the information gain from our level 2 equals E2 minus E1, where E2 is greater than E3. And as we come down here, we'll see that the E3 is now the third level where we split the oranges and apples out. And each time that entropy becomes less and less and less, until in this case we have an entropy of 0, since they're all homogeneous in their order. All oranges, all apples, all bananas. So let's take a look at the use case decision tree and actually put this into code and see what that looks like as we go from theory to script. And to predict the class of flower based on the petal length and width using R. And you'll see here we have these beautiful irises, probably the most popular data set for beginning data analysis and statistics. We have the Setosa, the Virginica, and the Versicolor. Let's install the packages that will help us in the use case. So because we're doing decision tree, we have rpart.plot, and then we have the library rpart and the library rpart.plot. Let's go ahead and take a look at that. And if you remember, we have two ways of installing it. We can do the install packages. We did that earlier. Here we go, install packages, using my up arrow to get to it. Or we can go up to Tools, Install Packages, and I can do rpart and rpart.plot, and then go ahead and hit the install. Packages that will be updated as are currently loaded. Oh, looks like some of them are already loaded. That's fine. We'll just go ahead and update those. And once we have those updated, let's take a look and see what we have going on here. Oh, it's still loading. Let's go ahead and type in library rpart and library rpart.plot. So we want to bring it into our console that we're working in. So up and now we just download the packages, and now we want those libraries available to what we're doing. So the iris, although it's built into the R package download on the basic download, we actually have to install the data or bring the data in. So we're going to do the data iris, and then we're going to do the string iris. And let's just flip back on over to our RStudio and set up our data iris, and then we're going to do string. Before we do that, let's do head iris. There we go. And you can see the head has sepal length, sepal widths, petal length, petal width, species. In this case, the top part's all Setosa, and each row gets a number. And then we did the string iris, and that comes up with information. And if we flip back to our slide, you can see here the structure of the database under string is it's a data frame. It has 150 objects, 5 variables each, so each one has 5 variables. All features are numerical except species, which is categorical as it is our target variable, which we want to predict. So we want to predict whether it's going to be a Varicosa, Versicolor, Setosa. So you can see here we want to predict all the features are numerical except species, which is categorical. It is our target variable which we want to predict. And you can remember that's the Setosa, the Versicolor, the Virginica, the 3 different categories we saw earlier in the beautiful pictures of the flower. And so we're going to go ahead and use the set seed to decide the starting point used in the generation of sequence of random numbers. Remember, we set the seed so that if we ever want to reproduce what we're doing, it will reproduce the same thing each time because it's using the same randomizer seed. Bring slightly different results, but depending on what you need it for. And then we're going to generate random numbers using runIf. And the question is, why do we want to create random numbers on here? It's kind of an unusual thing to do for nRows iris. And let's go back and just take a quick look here. Actually, we want to go back to our RStudio. And you're going to notice when I did the head of iris, what did I have? I had Setosa, 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 Setosa. So the data is organized by species, and it's already grouped them together in the data set. Well, we want to randomize that so that doesn't affect our output. And then we'll go ahead and take and create our iris ran, where we recreate the data frame based on a random order instead of Setosa all being grouped together. Let's go ahead and put that into our RStudio and set.seed, and we'll match their number. It's 9850. This way we'll have identical results to what they're doing on the slides. Then we're going to set the variable g equal to runIf and base this on nRow of iris. And finally, we're going to create iris underscore ran, and we're going to assign our variable we're creating iris underscore ran, and we'll set that equal to, we're going to do that to the original database, we're going to set that equal to iris, and we need brackets because we're assigning the variables, and we want to change the order. So there's an actual command order we can do. It's going to be order G. So this means all the rows in the order that G is. So we just randomized all those rows. And then we want to keep all the columns. We'll just put a comma and we'll leave it blank for the columns. So now iris ran will have some randomized rows coming in. And if we do head, let's just do this real quick, iris ran. We can see that it's no longer Setosa, Setosa. We now have Virginica, Setosa, Versicolor, Setosa. And you can see the row numbers at the beginning. We have 103, 20, 63, 17. So they're randomized on there pretty well. Now that we've done a little data manipulation, we can go ahead and build our model using rpart as follows. And one of the things I want you to notice here is we're going to build our model for our R part on the first 100, because our data equals iris ran 1 to 100. There's 150 objects, so we're keeping a third of them off to the side. That way we have our training set and our test set already pre-built because we randomized the rows going in from the beginning. And then once we've done that, we want to go ahead and print our model out and take a look at it. Let's go ahead and put this into our RStudio and take a look. And so we have our model. We're going to call it model. That's our variable name that we're giving it. We're going to assign that our part. And in brackets, we'll start with species, and we want to correlate species to all the other columns. So how do we do that? And the shorthand is just to put a period there. And then we're going to put a comma, and then we want to set our data equal to iris ran. That's the data we put in there. And remember I said we're going to do just the first 100 rows, so we can save the last 50 for testing. So we can do that simply by doing row 1 to 100. So in R you start with 1 for your rows, and because we want all the columns we just put a comma, and that denotes that we're going to use all the columns in here. And in the R part there's different methodologies. We're using the method equals class. And you realize that we're doing a classification between the 3 different types of flowers, and so this is what we want to go ahead and set up our model with. And when we run that, we've now created a nice model for us. We can go and just type in model, hit enter, and you'll see it'll print out a bunch of information about our model to let us know what's going on in there. And let's just break that down and see what that looks like. So we have our target, our predictors, that's species, and it's going to relate to, we used a period to denote all the columns. We're going to take the first 100 rows to train the data, and we have the defining method to be used as classification. That's what the method equals class is. And what we want to do next is we're going to do a plot and take a look and see what this actually looks like, a little visual here, which is nice. And we simply do that with our plot for the model. And let's break this down a little bit and just see what that looks like in the R setup. And we do this rpart.plot. A little bit of a mouthful there sometimes. That's part of the rpart package or module. So when you imported this in, it also included its own plotting format. And we're going to send it our variable model. And there are actually a number of types of plots listed for rpart, but we're just going to do type equals 4, fallen.leaves equals t, and extra equals 104. Let's go ahead and hit enter on there. And you'll see right over here on the right hand side it goes into our plots. We just enlarge that. We have our versicolor, our setosa, versicolor, virginica. And let's go ahead and break that down. As you can see down here, it represents the tree as it splits. It looks at it and says, hey, if the petal length is less than 2.6, it's going to be a setosa. So 34% of them fall into that category. And if the petal length is greater than 2.6, then looks at that and says, okay, now I have 3 different variables. We're going to split it again. Petal width is less than 1.7. It's going to be a versicolor, and if it's greater than 1.7, it's a virginica. And so you can see here, it's a very simple tree it forms. It's only got a couple levels. You can see a branch off to the right. Very nice depiction of what's going on as far as the model now that it's created. But once we create the model, we need to figure out, is this model any good? So let me go back over here and let's go back to our slides. And the first thing we're going to do is we're going to take our test data. Remember, we saved 50 rows for the end to go ahead and run a predict on there. So let's go ahead and run that prediction. So we'll call it model_predict. And we're going to hit a wrong button there to predict. And what are we going to predict? We're going to predict our initial model. And we need to send the data. So data equals. And we don't actually have to put the data part in. We just put in iris_ran. And then we want to do just the last 50 rows. And we denote that by 101:150 and then comma. And we'll leave that part blank since we want all the columns to show up. And then finally, this is a classification. So we need to let it know that type equals class. There we go. And let's just see what that looks like. Model predict. And so this is what the data is put out as. Is it says whatever this is, 131 is a virginica, number 10 is a setosa, line number 95 is a versicolor, and so on all the way through. What we really want to know is how good our model is. So we're going to go ahead and install a couple more packages. We're going to install the packages required to use the confusion matrix. And to do that, we're going to install caret and E1071. And then, of course, we want to set them to our project by using the library command. And so we can simply install packages, and we want caret, and we'll go ahead and just do that right there. There's Caret installed. And we went ahead and did the install for packages E1071. See, it goes through there. It's a really quick install compared to the Caret. And then once we've installed the packages, we need to load it into our workspace. So there's our library Caret. Oops, I should load it in there. There it goes. And once that's loaded, we'll go ahead and also load or set the library to the E1071 so that we have both those libraries available to us. And here we go, library, and then this one is E1071. And now these two libraries are fully available to us. And then we're going to use these tools to create the confusion matrix. And this one, confusion matrix, this is the iris ran. And then we'll go ahead and put the brackets here. And we're only going to do 101 to 150. And then we only want the first 5 columns, not the last 5 columns, the first 5 columns. So 5 in there. And we'll set that to our model predict. And then when we hit enter, it's going to head and just print out all this information. So right here, we're looking at our confusion matrix to see how everything kind of balances out. Let's go over that and see a little closer what that actually means. So the first part we see is a reference. And in here we have our prediction, because that's what we call it, the column, if you remember correctly. And we have it for Setosa, Versicolor, Virginica, and then we have Setosa, Versicolor, Virginica going down each side. And the way you read this is if you look at this, we predicted 16 out of 16 Setosa. And then Versicolor, we predicted 13 of the Versicolor, and then 2 of those we predicted as Virginica. So we were wrong on 2 of those. And with the Virginica, we predicted 17 correct, and we had 2 wrong that were Versicolor. So we look at the overall statistics on here, and we have an accuracy of 0.92 and a 95% CI. That's pretty good as we're going through here. Those are good deals on that. And there's a lot more information as you go down this. The one thing I want to remind you on this as we're looking at these predictions, and this is also true for the linear regression model we looked at earlier, when we talk about the accuracy, that is the accuracy on this data. And we say that as a programmer to make that a very clear distinction, because if you're in data analysis, you should cringe if I say, this is a 95% accurate model without that put in there, because bad data in, bad data out. We won't go into detail right now on that, but that is very important to note that whenever you quote any of the accuracies on here or you discuss any of these values that come up. So a quick summary, introduction to R. We went over the fact that you can import data very easily from a table, an Excel spreadsheet, a CSV file, and you can also export it. We went over the regression line of best fit and how those formulas work to slowly adjust that line until it fits with the least amount of error. We discussed correlation analysis in R, where we're correlating data between 2 objects. And then we talked about the decision tree algorithm and model building and validation. Thank you for joining us. For more information, visit www.simplylearn.com. Get certified, get ahead.
Hi there, if you like this video, subscribe to the Simply Learn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.